Okay, so we were looking at the cardiac nodes and how they had a different inherent rate, and we saw that the SA node had a rate of about 70 to 100 beats per minute, and the AV node had 40 to 50 beats per minute, and the ventricular nodes are 20 to 30. And then we said that the fastest node sets the speed for all the cardiac muscle cells. So the SA node is normally called the pacemaker, and through a process called overdrive suppression, the fastest node that's functioning inhibits the slower nodes. So if all of them are working, the SA node sets the basic rate, and your heart rate will be about 70 to 100 beats per minute. If the SA node's not functioning, the AV node is, then your rate would be 40 to 50 beats per minute, and that would suppress the ventricular node. And if neither of the two are working in the atria, then the ventricular nodes would take over and your heart rate would be about 20 to 30 beats per minute. Again, you wouldn't be entirely very healthy, but you'd still be alive, which is important from an evolutionary point of view. Um, Overdrive suppression works fairly well. The faster the heart rate, the better suppression we get. But the ventricles can be impatient at times. And if you do that, you see oftentimes what happens is a premature ventricular contraction. This is a contraction that happens early, hence the name premature, and it comes from the ventricles. On medical shows and medical terminology, they often refer to it as a PVC, and that's when the ventricles beat early. The problem when the ventricles beat early is that filling time has been shortened and the volume of blood pumped is going to be less because of that, and that could create problems, especially somebody who has an abnormal heart already. It's caused by a number of different things. One of those could be a reduced sinoatrial node firing, so you have a low heart rate already. That depresses the overdrive suppression, and the ventricles don't get suppressed enough and they fire. Stimulants can do it, so caffeine or cocaine. Some people feel when they drink a lot of coffee, they can feel their heart skip a beat. That's what a PVC is. You don't feel the actual PVC, but there's what they call a compensatory pause after it, and people feel that pause. So if you ever felt your heart skipped a beat, you've probably had a PVC. And because of the reduced overdrive suppression, athletes who we talked about way back in lab 2, generally tend to have a lower resting heart rate. They tend to have a significant number of PVCs sometimes. And again, in a healthy person, a PVC is probably not a big deal at all. But in someone who's already got compromised heart and have cardiovascular disease, then it's certainly a much bigger issue. A couple other things we can use to describe heart and heart rate. While your average heart rate, most people say is between 70 and 100, we saw in lab, there's a number of people that have heart rates in the 60s and even 50s normally. And we can have names for all of those. So if your heart rate below 60, it's called bradycardia, right? So Brady, as in that old TV show. Most of you probably aren't in the right demographic, but Brady Bunch, right? So bradycardia, right? So Brady means slow, cardia, heart. It could be a genetic thing where you just have a slow SA node. It could be you have a very active parasympathetic nervous system, which would decrease your heart rate. It could be you have a disease, or it could be that you're an avid exerciser and they increase the stroke volume, so you have a lower heart rate. It's kind of like I mentioned before that Lance Armstrong has had his heart rate measured as low as 24 beats per minute when he was in excellent shape. We say that 60 to 100 is usually normal heart rate range, and then anything above 100 is tachycardia. So I always say, like some of you dress, tachy means quick or fast. So tachycardia would be a fast heart rate, anything above 100. Now, we sort of talked about this a little bit, but we'll connect it together a little more formally now. And that's the basic heart pattern. How do we get the electricity through the heart and make it work? So we'll kind of put it all together in one package here. As we said, under normal circumstances, it's the SA node, so right up here, right? The SA node is the pacemaker. It's the one that spontaneously depolarizes. When it does that, it sends the wave of depolarization, that's number 2 right here, so you can see the purple, through the atria. From the right atrium sort of goes kind of down, but in the left atrium it goes across and then down. And again, what it's going to do, it's going to help to contract the atria from the top down. So we're squeezing them and pushing them towards the ventricles. All right. Once the electricity gets through the atrium, the right atrium, at the bottom of the right atrium, we have the AV node. So if you look at the third picture here, right, that gets the electricity, and it collects the electricity. It actually slows the conduction down a little bit in this case, and that gives us a chance to physically contract the atria and push the blood into the ventricles. Remember, this electricity is going to precede the actual contraction and then the movement of blood. Once we get to the AV node, we go through what's called the bundle of His. It's spelled His, so you can see it over here, His, right? But it's pronounced His, like a sound a snake would make. And the bundle of His branches to two sides. One is the right bundle branch, the other one is the left bundle branch. So we can see it down here in the fourth one. So you can see the two little purple lines. Those are the bundle branches. So there's two bundle branches. And then each bundle branch then curves up and goes into what we call Purkinje fibers. Purkinje did a lot of histology. You probably might have studied Purkinje cells in like the cerebellum before. So my Purkinje fibers are what actually allow the electricity to be passed directly to the ventricles. And then once the Purkinje fibers do that, then the ventricles are electrically coupled like they were in the atria. What it does is it pushes the electricity from the bottom of the heart up. And that allows the ventricle to contract from the bottom up, which helps to push the blood out the large vessels out of the top. So that's the conduction system of the heart. Best way to think, again, is a kind of summary. SA node, AV node, the bundle of His, so sometimes known as the AV bundle, the bundle branches, and the Purkinje fibers, and then you get ventricular contraction. So that's how the conduction system works. Now we can measure to a large extent that conduction system by what we call an ECG. Okay, so ECG stands for electrocardiogram, lab 24. We'll also look at ECGs in a little more detail. So the E is electro, the C is cardio, the G is gram. But in the United States, we still use the term EKG just as much. It also stands for the same thing, electrocardio with a K, gram. The reason why we still use it in the U.S., even though we don't typically spell cardio with a C, K, we spell it with a C, is because it was confused earlier when most of the medical instructions were verbal, not written, with ECG. And if you said, go do an ECG, it might have sounded to someone like an EEG, and looking at the brain waves when you want to look at the heart waves is certainly not the way to go medically. And K was very spelled differently, sounded very different. I think that's part of the reason why we still see it. So they're used interchangeably, so don't get confused. ECG is the same thing as EKG. They're very useful medical diagnostic tools. They're non-invasive. It means we don't have to stick anything in anybody. There's no needles. You just put some electrodes on the outside. They're completely safe. And what it does is it measures all of the summed electrical activity within the cardiac cells. So we're going to be able to follow that conduction system we just talked about on the ECG. What's interesting, though, is the electrodes are not on the heart itself. They're actually, we can measure it, and we've done this in lab, on the limbs. And so you could stick an electrode on the right arm, you could stick one on the left arm, and you could stick one on the left leg, right? And then we'd also have one typically on the right leg that would be a ground. Those are called limb leads because they're on the limb leads. Don't worry about Einthoven's triangle. But when we have done lab, we've stuck an electrode, the white one, on the right wrist, and then we've stuck one on the left leg. That's our positive electrode. And then we've had the ground here. What we've done is we've looked at the relationship between these two electrodes, and that gave us the electrical activity of the heart, primarily focused on the left ventricle, which is the most important of the heart chambers because it's the largest, it needs the most oxygen, it does the most work, and it's more likely to have the biggest problems if there's some sort of disease process because of those needs for higher oxygen, higher blood flow, and more work. So how does it work that we can put electrodes on the limbs and still measure what's happening in the heart electrically? Well, it's a process over here called volume conductance. And that means the electrical activity of the heart is passed through the blood, primarily through electrolytes. So it's called volume conductance. And we're not going to look at it in very much detail at all, not even so much detail in the laboratory portion when we look at the ECG. But it'll give us, you can measure heart rate. That's what we've used it for this semester. You can see if someone's having a heart attack. That's called a myocardial infarction, right? That's a scientific name for it. You can tell if someone has had one previously. You can look to see that conduction system, if it has abnormalities in it. You can see the different size chambers of the heart. You can see what direction the heart is pointing in. So there's a lot of diagnostic information you can get from an ECG. The more electrodes you put on somebody, the more diagnostic information that you can get. So here's sort of a basic ECG, and this is how a normal one looks. When we measure the ECG, this kind of looks like one, and actually, to be honest, this first wave, this P wave, should be smaller in relationship to the T wave, but it's good enough for our purposes. So there are 5 distinct waves that make up an ECG. There's actually a sixth one that you very rarely see called a U wave, so we won't worry about that. But the first wave is called the P wave. Okay, and I've always wondered why they called that the P wave. It never made sense to me, especially when we talk about what it corresponds to. But the reason why it's called the P wave is the first person to actually do an ECG was a German physicist by the name of Augustus Waller. And he actually measured it on his dog. It was a bulldog. I don't know why I remember this, but named it Jimmy. And what he did is he stuck the bulldog and had him stand in 4 buckets of salt water with wires on each one, and was able to measure the electrical activity of the dog's heart. So that's why it's called EKG, because in German you spell cardio with a K. But since he was a physicist, I guess physicists are trained, especially the time when he did it, if they find an unknown vector mathematically, and the ECG is actually a series of vector waves, to name it P. So that's why the first wave is called the P wave. And then everything else follows through it, right? So the next wave, which you probably won't see on most people because it's not very prominent, is called the Q. The big wave going up is called the R. The little wave going down is called the S. And then there's a big wave after that's called the T. And it just goes P, Q, R, S, T. And then just repeats itself for that. Way back in lab 1, we had an exercise to measure what's called the R to R interval. That's the space between the 2 waves. And the R to R interval, if we measured the time, we could use the inverse of that and measure a rate and figure out what the heart rate was from that exercise. So the R to R interval, that corresponds to, not surprisingly, when the ventricles are contracting. So let's kind of look at it from the beginning. And again, this is probably the level of detail you have to know for lecture, and certainly this would be important for lab too. So if you know it once, you'll know it for both places. So the P wave corresponds to atrial depolarization. That's with the electrical activity moving through the atria, right? So the P wave is actually a determinant of what's happening in the SA node. And if the SA node isn't firing, you're not going to have a P wave. So the P wave tells us the SA node is functioning. Okay. The next one is called the QRS complex. We put those 3 waves together. So if you look down here, right, we have the Q, then the R, then the S, and we put those together in QRS complex. And there's actually 2 things that are happening here. The ventricles are depolarizing, which means the electricity is going through the ventricles. We see that here, right, in these. But also, what's also happening at the same time is, since the P wave was atrial depolarization, Once you have depolarization, you have to have repolarization. So the QRS complex, also hidden in that, is atrial repolarization, where the atria are resetting basically and getting ready to fire again. So that's an important component. And then the last one is the T wave, and the T wave occurs when the ventricles repolarize, right? So they need to reset, and that's why you see it. So the end, if you look up here at the upper left of this diagram, right, you see P, Q, R, S, T, and look at those different waves that correspond to different portions of the heart. There are a couple things that probably kind of look at, and just to kind of make this point. One of them is we can divide the heart into different sections, okay? And we're going to talk about that in a minute with the cardiac cycle. But one of the things, as an example that we want to look at, would be atrial systole. That is when the atria are contracting. That's important. That's when they're ejecting that last 1/3 of blood from the atria to completely fill the ventricles. And so that occurs from about the peak of the P wave to not quite, but pretty close to the QRS. Remember, it's the electrical activity that has to happen first in order to get the muscles to contract, which then pushes the blood, right? So you have to have the electricity correspond to that portion. Actually precede it, I guess, is a better way to think about it. So atrial systole, right, is from the P wave to somewhere in the QRS complex. And then ventricular systole, when the ventricles are contracting, happens, the best measurement is from the peak of the Q wave, right? So right here where it's purple, to the end of T, okay? So that's called the QT interval, right? Don't ask me why, I don't want to go into it, but even though it's the peak of R, they call it the QT interval, and that corresponds to ventricular systole. Since there's only two options in the heart, it's either contracting or relaxing, and we'll see that we can subdivide those options in a little more detail for the cardiac cycle. But then the ventricular diastole, when the heart is resting, would be the corresponding inverse of that. So the end of T to the peak of Q would be diastole. Okay, and that's not surprisingly called the TQ interval, although most people don't use that term. So one of the things I want to kind of look at here, and this is going to be important in lab and maybe a little bit in lecture when we talk about calculations of things. Notice the QT interval. This is pretty, representative of what an ECG would look like. It's pretty short. So notice this time, right? We're not going to actually measure the time, although we could, right? This is, 100 to 350 milliseconds. So that's about 250 milliseconds here, right? And then if we look at this, we go from, 0 at the peak of P to 800 at the peak of P, and 100 to 900. So there's 800 milliseconds here, of which 250 or so is systole, which means diastole is that other difference, which is be what, 550. So 550, so more than twice the time for diastole than we have systole. And so here's something to put in your head. This is an important fact, which is we're going to use this idea a lot in our calculations, is that at rest, normally, most humans spend about 1/3 of the time in ventricular systole when the heart's contracting, and about 2/3 of the time in diastole for the ventricles when the heart's relaxing. That's going to become important when we calculate mean arterial pressure, because mean arterial pressure is the average blood pressure over time, and we have to take this time incremental difference into account in order to calculate mean arterial pressure, which is your average blood pressure over time. So one of the ways we can look at that is through the cardiac cycle. All right. So, and that's, again, before we move on to the cardiac cycle, that's about all you have to know for ECG for lecture. I don't think we need to know that. And for those of you that need to know it in your job, most of the ECG is now done with an automatic analysis that actually is done by the machine that's recording it, and the machine picks out abnormal or bad rhythms or things like that. And in most cases, literally texts a cardiovascular specialist that's online at the time and says, here's the problem, what do you want us to do, basically. So there's much less ECG interpretation by clinical specialists like nurses and things like that now than there used to be. And if you do have to do that stuff, they will teach you how to do it. So but understand a little bit about ECG, like we talked about, is probably good. So be able to identify the waves and what they correspond to, and make sure you understand the 1/3, 2/3 thing for lecture, and you should be good. The other thing that we need to look at a little bit is called the cardiac cycle. The cardiac cycle explains what stepwise progression we go through in order to have the heart contract and relax. So one complete cycle. In general, the cardiac cycle can be broken up into two basic things. We're not going to worry about this numbering system here. It's atrial systole and diastole, and ventricular systole and diastole. And obviously, they're going to overlap. When the atria are contracting, right, the ventricles have to relax. And when the ventricles are contracting, the atria have to relax. But they both, we'll see, they both can relax at the same time as well. So remember, systole is when we contract, and diastole is when we relax. So we're going to go through, it's going to be called the 5 phases or stages of the cardiac cycle. Okay, and again, it just explains the relaxation and contraction of the heart, how it goes through systole and diastole, what happens to the various valves, what happens to blood flow, and things like that. By convention, these are often numbered phase 1, 2, 3, 4, 5. So the 5 phases or stages have numbers. Although it's a cycle, theoretically, you could start anywhere. This is where typically they start. Phase 1 is known as late ventricular diastole, right? Also, the atria are in diastole at this time, so both chambers are relaxing. Okay, the goal of this part of the cardiac cycle is to fill the ventricles. Okay, and so what happens is blood, we'll go up here where it says start, blood passively is flowing back to the atria. Because the atria are relatively small, as blood flows in, the pressure of the atria go up as we put more blood in it. And the pressure of the atria is going to be slightly higher than the pressure of the ventricle. We mentioned earlier, keep this in mind, blood moves because of pressure differences. So when the pressure of the atria exceeds that of the ventricle, then blood's going to move in. Okay, so I don't want that yet. And as blood moves in, that's the passive flow of blood from the atria to the ventricle. Okay, and about 2/3 of the blood that flows from the atria to the ventricle flow passively, to be honest. And it's only about 2/3 of that's probably somewhere around 50 mils or so of blood that just flow passively. This is a large portion of the cardiac cycle where both the atria and ventricles are relaxing. What's going to happen during exercise is this is going to decrease in duration as we move blood faster through the body. When you're exercising, we'll move blood faster here, so the pressure will increase higher and faster, which will increase the passive flow here, so we can also fill the ventricles easily, to be honest, and make sure we get enough blood in them to pump. And we'll see the other ones as well. The other thing to note here, right, is since blood is passively flowing from the atria to the ventricles, the AV valves have to be open, right? So both the AV valves have to be open. Whatever happens on the left side happens on the right side, okay? And in order for the ventricles to fill, the semilunar valves must be closed, okay? So otherwise the blood would just flow out the other way, right? And just to go through it, we have 4 valves in the heart. There is never a physiological situation where you're going to have all 4 valves open. We could have one set of valves open, one set closed. We could have one set closed and the other open. We could have both sets closed, but we'll never have a situation where we have both sets open. So in this case, so we can fill, the AV valves are open and the semilunar valves are closed. All right, so that's late ventricular diastole. Atrial systole is the second stage. And during this time, this is when the atria contract. So this is sometimes referred to as the atrial kick. Right? And that's when the last 1/3 of blood, remember 2/3 was passive, so this 1/3 is active, is pushed into the ventricles. So again, if your atria never contracted, would you get blood to the ventricles? Yeah. And would the ventricles pump to the body? Yeah. And would you be alive? Yeah. But you certainly wouldn't be able to do certain things like, walk from the parking lot to class when school was in session. So that's called the atrial systole. The ventricles are still relaxed at this point in time, so they can fill. Right? We're still moving blood from the atria to the ventricle, so the AV valves are still open. Right? So our AV valves right here still open. The semilunar valves are still closed. Right? But this time, instead of being a passive process, it's going to be an active process. All right? So that is phase 2. Now, in phase 2, there's a couple things that we can kind of bring up in terms of information that we think is important. In terms of phase 2, we can measure something called the end diastolic volume. Okay, and it sounds confusing, but if you think about it, it really describes exactly what we're looking at. It's the volume of blood at the end of diastole, and that's going to be in terms of referencing the ventricles. So the volume of blood in the ventricles at the end of diastole is how much blood do we have in the ventricles before we pump it out. Okay, and there's actually 3 components to that. First of all, there's some there from the passive flow of blood. Okay. There is some from the active flow of blood during this atrial systole. This is the end of it, though. And I mentioned earlier in a previous video that there's some blood left in the ventricles even after we eject it. We're designed to do that. It's actually, we believe that it's easier to leave some in the ventricle instead of trying to squeeze them completely out and just fill the ventricle more the next time to get the sufficient amount of blood flow. And so that's what composes the amount of blood that we have in the ventricle, and that makes up the end diastolic volume. For our purposes in class, we're going to assume it's about 100. That's probably a little low for most people, especially like our medical model that we typically again use as a college age male who weighs 70 kilograms or so. So someone like Luke Skywalker, who would come pretty close to fitting that mythical medical model, would be probably closer to 135, 140 mLs. We'll use 100 because it makes math easy. It's easy to remember, things like that. So we'll say a typical end diastolic volume is 100 mLs. Okay? And the units would be mLs per beat technically because it's every beat. So phase 3 is called isovolemic ventricular systole. Okay? And again, it sounds really hard, but if we break it down, it's pretty easy. Systole means contraction. Ventricular refers to the ventricle, so this is ventricular contraction. So what does this isovolemic mean? Well, iso means the same, right? So we saw like for isotonic stuff, iso meant the same. And volemic is just what it sounds like. Sometimes it's spelled with an E, not a U. But isovolemic means the same volume. So what's happening in isovolemic ventricular systole is by definition, the ventricle is contracting, but there's no change in volume. How do we do that? How does that happen? Well, in the third phase, during isovolemic ventricular systole, or you could say contraction, same thing, right? The ventricles, right, have now received that input for the conduction system to say contract, right? So the electricity went through the ventricles from the bottom up, as we talked about before for the conduction system, and now the ventricles start to contract and generate pressure. As the ventricles generate pressure, right, the ventricles actually get smaller. They physically get smaller. So if you look from This one probably shows it better. Look at the size of this and look at the size of this. Because the volume, the size of the ventricle, right, is smaller, and the volume of blood is the same, the pressure of the ventricle goes up. So as we squeeze the ventricle and get it smaller, 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 the pressure of the ventricle actually goes up. And why it doesn't change volume is this, okay? So let's kind of go back to those pressures we talked about in the last video. The pressure of the atria, right, after it goes through its systole, right? So atrial systole was the last one, right? It probably went to a peak pressure of 5, and then once it ejected the blood, it went down to 0. And in case of the atria during exercise, it can actually go even less than 0 and become negative pressure. But it's going to go to 0. So as the ventricle starts to contract, right, its pressure starts to rise. Once the pressure of the ventricle exceeds the pressure of the atria, these semilunar valves, right, the semilunar valves, the aortic, the atrioventricular valves, the AV valves, the ones between the atria and the ventricle that were previously open during atrial systole, they snap shut, right? The valves on the outlet of the ventricle, the semilunar valves, both the pulmonic and the aortic, right, they're not going to open until the pressure of the ventricle exceeds the pressure of the outlet. So let's go with what we know on the other side. So the aorta, right, we know from average blood pressure readings, the aortic pressure is going to be 120 over 80. So 120 is the systolic pressure and 80 would be the diastolic pressure. So in order to eject blood out of the ventricle, because blood moves due to a pressure difference, the pressure of the left ventricle must exceed 80, the diastolic pressure of the aorta, or whatever it is. Okay? That's why one of the reasons why hypertension is so bad is now the ventricle has to generate a higher pressure to push blood out, right? So that pressure that we have to exceed, once it gets above the 80, now the pressure of the ventricle is greater than the pressure of the outlet and will eject blood. But that happens the next stage. So this stage is in between those two pressures. Once the pressure is high enough, which is basically anything above 0 in the ventricles, that snaps the AV valve shut, and the pressure hasn't built up high enough yet to open the outlet, the semilunar valves. It's a very short amount of time, okay, and that's called isovolemic ventricular contraction. That's physically when the ventricles are getting smaller and smaller in size, but the blood is staying as the same volume. And that's because, remember, the job of the valves is to prevent that backflow. Okay. To be honest, since it's isovolemic, the end diastolic volume, the EDV, is the same because nothing's changed by definition. So now we get to phase 4. That's this one on towards the bottom left, and that's called ventricular ejection. In ventricular ejection, this is when blood is ejected out of the ventricles, right, into the outlet. And it depends. The right ventricle would go into the pulmonary trunk, and the left ventricle would go in the aorta. And so in order to do that, you have to get the pressure of the ventricles, pressure of the ventricles high enough where the ventricular pressure exceeds outlet pressure, right? And so that's called ventricular ejection. And we eject, somewhere between 70 and 80% normally of the blood that was in the ventricle. We'll kind of see that idea in a sec. All right. And before we get into those numbers, let's go look at the last phase then. So going back here. In this phase, right, since we're moving blood, blood is going from the ventricle into the outlet, right? That means the semilunar valves have to be open and the AV valves would be closed, right? So another example of 2 of the valves, one set, are open, and 2 of the valves, one set, are closed. Okay. Once blood is ejected, and most of the blood is ejected, and the ventricles start to relax, then we're into our last phase, isovolemic ventricular diastole. So it's the exact same of isovolemic ventricular systole, but instead of generating pressure, we're reducing pressure, right? We're in relaxation. So what happens here is the muscle has contracted, it's pushed out blood, and now the muscle relaxes. And now the chamber size gets bigger. There's a very small volume of blood in it, so the pressure drops down close to zero. So once the pressure gets below outlet pressure initially, the semilunar valves close. And it's not until the pressure gets pretty close to zero, where the atrial pressure is again higher than the ventricular pressure, where blood starts to flow. So in this case, we see all the valves are closed. The AV valves and the semilunar valves are closed. That's what gives it the isovolemic name, right? And now once they go down what they are referring to the ventricles, once the ventricles get down close to zero, blood starts again to passively flow from the atria to the ventricles, and we're back to that first time. Now, when we look at these things, we have other values we can measure, okay? And so in phase 5, that gives us the idea of isovolemic ventricular diastole, okay? And that's when there's no change in blood volume. So the blood that's in there has a specific name, okay? And that's called end systolic volume. So the end systolic volume is the volume of blood left in the ventricle after systole, so at the end of systole. So after we've ejected blood, right, the end diastolic volume is what's left. It's a highly regulated variable. It's about 30 mils usually in most people, right? So now we can figure out something else. We can figure out, which I don't have on any of these PowerPoint slides, something else. We'll see it a little later. And that's called stroke volume. Okay, and the stroke volume is the difference between end systolic volume and end diastolic volume. So the way to calculate stroke volume is stroke volume equals end diastolic volume, the volume of blood that you started with, minus end systolic volume, the volume that you ended up with. So the difference between those two would be stroke volume. So since our magic number for end diastolic volume, if you remember a couple slides ago, was 100 mils per beat, and the magic number for end systolic volume is 30 mils per beat, that means the stroke volume is the difference. 100 minus 30 is 70 mils per beat. There are also a couple other numbers that we can get from there as well that we'll look at in a little more detail later. So the complete kind of cardiac cycle all in one shot, right, would be phase 1 is atrial usually late ventricular diastole is what it's called. This is when the atria are passively filling the ventricles, the AV valves are open, the semilunar valves are closed. The second phase is called atrial systole. This is when the atria contract and push the last 1/3 of blood into the ventricles. So the first 2/3 came from phase 1, passive, right? In order to put blood actively into the ventricles, the AV valves have to be open, the semilunar valves have to be closed. Phase 3 is isovolemic ventricular systole. This is when the ventricles are contracting and generating pressure, but there's no change in volume. Since there's no change in volume, the AV valves and the semilunar valves are closed, so all 4 of the valves in the heart are closed. That leads to ventricular ejection. This is when blood is ejected out of the heart. That's called the stroke volume, the volume of blood that's ejected during that time. In order to do that, the AV valves have to be closed, but the semilunar valves have to be open. Okay, so that's ventricular ejection. And then the 5th phase is isovolemic ventricular diastole. This is when the heart is relaxing and the pressure is going back down pretty low so they can begin filling again. And during this time, we have the end systolic volume, the volume of blood that's left in the heart. And again, that's a highly regulated variable, and you leave about 30 mLs. And under the vast majority of conditions in a healthy heart, you leave that 30 mils. So as an example, we said end diastolic volume in a normal person was about 100, and the end systolic volume is about 30. So the difference is 70. That's your stroke volume. If you were exercising, let's say your end diastolic volume was 170, okay, then how would you figure out the other values? Well, we'd say, oh, since the end systolic volume is highly regulated, it's still going to be 30. So if we filled the ventricle with 170 mLs per beat and was left with 30 mLs per beat, that means your stroke volume would go up to 140 mLs per beat. So it's a highly regulated variable, and we'll talk about how that's regulated during regulation of heart rate for mean arterial pressure. This diagram you have to worry about, but it connects everything together. It's called a Wiggers diagram, and it shows the relationship between the ECG and what happens with the different pressure changes within the aorta and the left ventricle, right? And the atrial pressures on the left side, and then the end diastolic volume changes and end systolic volume changes for each one as well. All right, so don't have to worry about it, but if you're kind of interested in how that all lines up, you can kind of see that there. One last point that I want to make, and then we'll start a whole new set of videos for the vessel stuff. One of the things that students, I don't think, really understand, so I want to be very clear on this. The left ventricle and the right ventricle pump, in normal circumstances, the exact same amount of blood. Okay? And if you thought about it hard enough, you'd say it'd have to be that way. Otherwise, all the blood would eventually end up on one side of the body. So even though the left ventricle generates more pressure, and even though the left ventricle has to overcome higher pressures, that's the reason why, the left ventricle and right ventricle have the same volume each beat, beat to beat for the most part, for your heart to work. So they pump the same amount of blood even though they work at different pressures, and that's something to remember. That's important. Okay, so that kind of cleans up everything from this section, and then we'll start a new section on vessels and other things.